Module 6. Lecture B, dir Vars help. By the end of this lecture, you will be able to use dir to list attributes of objects, modules, and classes for exploration and debugging. Apply Vars to inspect and manipulate _dict mappings of objects and modules when appropriate. And invoke help to access built-in documentation and understand signatures and usage of functions and types. Exploring objects with dir, inspecting module attributes. When exploring unfamiliar code, inspecting a module's attributes is a fast way to understand its structure and purpose. A Python module is a container that holds functions, classes, and other elements, and introspection tools let you see what it makes available. This gives you a quick snapshot of its capabilities, such as data loading functions or modeling classes in a data analysis module. This kind of overview is especially helpful when you join a new project or start using a third-party library. Inspecting a module's attributes is a useful way to debug and understand how that module is structured. If you expect a helper function in a utilities module but get an error, checking the attributes can show whether the function exists, has a different name, or is only imported under certain conditions. This becomes especially important in large or dynamic systems where modules can change at runtime, such as when plugins add new attributes. By comparing a module's attributes before and after certain actions, you can see what changed and better understand how configurations or feature toggles are affecting the system. Regularly checking a module's attributes helps you understand how a library is designed and how it changes over time. Comparing attributes between versions can reveal new features and deprecated elements. In data engineering, inspecting configuration modules helps confirm that settings such as database connections are correct. Educators can also use module attributes to illustrate ideas like namespaces and encapsulation. Overall, this practice trains you to focus on interfaces and contracts and gives you a clear view of what a module provides while it is running. Python code, inspecting module attributes. Use the dir function to inspect a module by listing all of its attribute names, which lets you quickly see what the module contains. When you call this function on a simple example module, you get a list of its current contents that you can explore. If you then add new names at the module level, calling the function again shows how the list of attributes changes. Comparing the lists before and after adding names demonstrates how module attributes are updated and how dir reflects those changes. We start by importing the math module and getting it a short alias so it is easy to recognize whenever we use its functions later in the code. We also import the types module with its own alias. This second module lets us create simple objects that behave like modules, which will be used in a later part of the script. The code first uses a directory listing function to show some of the available attributes in the math module, displaying just the first few as a sample. This gives a quick view of what functions and constants the module provides. It then checks whether the list of attributes includes one named pi. Finding pi in this list confirms that the module contains the expected mathematical constant. We use the simple namespace tool from the types module to create a basic object that behaves like a module, meaning we can freely add attributes to it. We then add an attribute called miles per hour and set its value to 60. This value represents a car's speed, showing how simple namespace can hold related pieces of data. Overall, this approach lets us organize information in a flexible, module-like object without creating a full module file. We set the road length miles attribute in the simple module to 120, representing a road that is 120 miles long. After assigning this value, we use the directory inspection function to list all attribute names in the simple module. This list shows everything that has been defined inside the module-like object. In this way, we both store a specific piece of data and then explore the module's available attributes. To find the trip time, we divide the road length in miles by the car's speed in miles per hour, which gives the number of hours the trip will take. We then store this value as a new attribute called trip hours in the simple module. Finally, we verify that this attribute was successfully added by checking that trip hours appears in the module's list of attributes. This script shows how to inspect and modify module attributes using the dir function. It first imports the math module with an alias and lists some of its attributes, confirming that the constant pi is available. Then, it creates a simple module-like object, adds attributes to represent a car's speed and a road's length, and computes the trip duration by dividing the road length by the speed. This result is stored as another attribute. Finally, the script checks that this new attribute exists, demonstrating how module contents can be explored and extended dynamically. Inspecting object attributes. When you work with a class instance, introspection tools let you see what the object can do by listing its attributes. This gives you a quick view of its data and operations, such as whether a customer object includes things like a shipping address or purchase history. This is especially useful in large code bases with third-party objects or when debugging complex behavior. Instead of searching through source files, you can directly query the object to understand its structure and capabilities. Inspecting an object's attributes helps you distinguish between its stored data and its available actions. For example, a bank account object might have data like balance and account holder, and methods such as deposit and withdraw. Seeing these together gives you a clear picture of what information you can access or change, and what operations you can perform. This is especially useful during debugging, because it can reveal missing or unexpected attributes, such as an uninitialized balance or a method you assumed existed but does not, highlighting mismatches between your expectations and the actual implementation. Inspecting an object's attributes can reveal dynamic behavior that is not obvious from reading the code alone. Some objects add or change attributes at runtime in response to configuration files or user input. For instance, a data processing pipeline might gain new attributes as it moves from raw to cleaned to summarized data. By checking attributes at different points in time, you can see how an object evolves, verify that certain steps have run, and detect missing or unexpected attributes. This is especially helpful in interactive environments like notebooks, where it supports understanding complex abstractions and debugging more effectively. Python code, inspecting object attributes. Use the dir function to inspect an object and see all of its available attributes. This list will include both data attributes, which store values, and methods, which are functions attached to the object. Clearly distinguish between these two kinds of attributes so you understand which parts hold data and which parts perform actions. After you modify the object, call dir again to observe how its attributes have changed, reinforcing how object state and available operations can be updated over time. We define a class called bank account to represent a simple bank account. Inside it, we use a special initialization method or constructor that runs automatically when a new account is created. This method takes the account owner's name and a starting balance, then stores them in instance variables for the owner and the balance in dollars. As a result, each bank account object has its own specific owner and current balance, forming the basis for any future operations on that account. The deposit cash method increases the balance of a bank account by adding money to it. It takes one input, the amount of dollars to deposit. Inside the method, this amount is added to the current balance. As a result, the account's stored balance is updated to reflect the new, higher amount after the deposit. The withdraw cash method takes an amount in dollars and subtracts it from the account balance. By doing this, it directly changes the balance attribute of the bank account. After the method runs, the balance reflects the new total remaining after the withdrawal. We begin by creating a new bank account object to represent a sample bank account. This account is set up with an owner named Alice and an initial balance of $150. With this example in place, we can focus on how to view and change the attributes of an object in Python. The account serves as a simple, concrete case for exploring how object data is stored and modified. We begin by printing a message to indicate that we are about to inspect the initial attributes of the bank account object, so we understand its current state. Then we call the directory function to get a list of all attributes and methods associated with this object. From that list, we remove the special items whose names start with double underscores, so we keep only the user-defined attributes and methods. Finally, we print this filtered list to see which attributes belong to the account object before making any changes or performing any operations. The program uses the bank account object to call a deposit cash method that adds $25 to the current balance. This action changes the account's internal state by increasing its balance value. It illustrates how calling a method on an object can directly modify that object's stored data. In this example, we add a new attribute to a bank account object to represent its overdraft limit in dollars. This attribute was not originally defined in the class, but Python allows us to attach it later while the program is running. By setting this overdraft limit, we control how far the account is allowed to go into a negative balance. This illustrates Python's flexibility in letting us modify objects at runtime by adding new attributes when needed. We first print a message to signal that we are about to inspect the account object after making some changes. Then we use a list comprehension with a function that lists all attributes and methods of the object. And we filter out any names that begin with double underscores, since those are special or private. This leaves us with only the user-defined attributes and methods, including any that were added dynamically, such as an overdraft limit. Finally, we print this filtered list to show the current state of the account object's attributes after the modifications. we print a summary of the bank account's main data: the owner's name, the current balance in dollars, and the overdraft limit in dollars. By reading these values directly from the account object, we can observe the account's current state. This snapshot shows the results of all previous operations and modifications made during the program's execution. This script uses a simple bank account example to show how to inspect and modify object attributes in Python. It starts with an account for Alice that has an owner name and a balance, and uses a directory listing to view these initial attributes. After a deposit, the script adds a new overdraft limit attribute to the same object. Listing the attributes again reveals this new property, and the script then prints the updated owner name, balance, and overdraft limit. Overall, it demonstrates that Python objects can have their attributes dynamically added and accessed at runtime. Discovering dunder methods. When you inspect an object in Python, you will see many names with double underscores, called dunder methods, which control how the object behaves in core operations like iteration and comparison. Looking at built-in types, such as lists or at your own classes, reveals these special methods alongside normal attributes, showing that there is a rich protocol behind everyday actions in your code. This helps you realize that objects do more than just hold data. They actively participate in a language's rules. Understanding this is important for seeing how your program actually carries out operations. As you practice introspection, you will start to connect specific special or dunder methods with familiar behaviors in your code. Some of these methods make objects iterable, others control how they are converted to readable strings, and others define comparisons like less than or equal. By examining an object, checking its documentation, or experimenting, you can see which methods are responsible for which behaviors. This is especially helpful for debugging because it explains issues like why a custom type will not sort correctly or why it prints in an unexpected way. Noticing which special methods are present or missing gives you valuable insight into how an object behaves. Using introspection to explore special double underscore methods is a powerful way to understand unfamiliar libraries and frameworks. By inspecting objects, such as dataset columns or web request objects, you can see which magic methods they implement and learn whether they support iteration, arithmetic operations, or use in context managers. This reveals the design intentions of the library authors and makes these abstract protocols more concrete. Over time, this practice builds a strong mental model of how objects are meant to behave, improving your ability to both use and design types effectively in the language ecosystem. Python code. Discovering dunder methods. Use the dir function on simple objects to reveal their double underscore or dunder methods, and then connect these hidden names to everyday operations, such as getting an object's length or converting it to a string. Show that when you call length or print an object, Python is really using these underlying dunder methods. Finally, compare how a built-in list behaves with a custom class that implements a few of the same dunder methods, so learners can see how defining these methods lets their own classes integrate smoothly with Python's standard operations. We begin with a simple example, a list of daily temperature readings in Fahrenheit containing 4 values, 72, 75, 70, and 68. This list represents a basic Python list object that we can use to study how lists work. In particular, it lets us explore the special built-in behaviors called dir methods that are automatically available to Python objects. These methods support many of the operations we can perform on the list. We use the directory function to see which attributes and methods are available for the temperatures in Fahrenheit list. This reveals the built-in features we can use with this list. It includes both the usual list operations and special methods that Python provides automatically. Exploring this helps us understand what actions we can perform on the list object. This code uses a list comprehension to scan all attributes of a list object and keep only those whose names start with double underscores. These names correspond to special methods, often called dir methods. By filtering for these names, the code identifies the internal methods that Python uses to implement many built-in behaviors and operations on lists. We show only a small sample of the special double underscore methods that belong to a list object. This limited view keeps the output from becoming cluttered and makes it easier to focus on a few methods at a time. By concentrating on a manageable subset, learners can better understand how these special methods work without being overwhelmed by too much information at once. We create a class called bank account to model a bank account with a dollar balance. Its initialization method takes the account owner's name and a starting balance as inputs. These values are stored in two instance variables, one for the owner's name and one for the balance in dollars. This design lets each bank account object keep track of its own owner and balance, forming the basis for adding more banking features later. This method controls how a bank account object is turned into a string. Whenever the object is printed or used where a text value is needed, this method is called. It returns a clear, formatted description that shows the owner's name and the balance in dollars. This makes it easy to quickly see the current state of the account. This method defines the length of a bank account object by converting its dollar balance into an integer. In other words, when the length function is used on the account, it returns the balance as a whole number. This lets the account balance be treated as a countable quantity, such as the number of dollars in the account. It provides a simple way to interpret the account's balance as its length in relevant contexts. This method defines how two bank account objects can be added together using the plus operator. When one account is added to another, it creates a new account whose owner name is copied from the first account. The balance of this new account is the sum of the balances from both original accounts. This makes it possible to combine account balances directly in a simple and intuitive way. We start by creating two bank account objects from our custom bank account class, one for Alice with a balance of $150 and one for Bob with a balance of $200. These two accounts serve as simple examples to show how special or dir methods work inside the class. Using them, we can demonstrate behaviors such as how accounts can be added together and how they are displayed when converted to a readable form. We use the dir function to inspect a custom object, such as an instance of the bank account class, and see what attributes and methods it provides. This includes both regular properties and special double underscore methods that may have been implemented. By examining this list, we can understand what operations the object supports and how it is designed to behave. We use a list comprehension to filter the attributes of the custom bank account object. It loops through the attribute names we obtained with the directory function and checks which ones start with double underscores, the usual pattern for Python's special methods. Any name that matches this pattern is added to a new list called account dunder. This gives us a focused list of the special or dunder methods defined in the custom class. We display a small sample of the special methods, also called dunder methods, for the custom bank account object. These methods show which built-in operations the object supports, such as how it can be represented or manipulated. By limiting the output to just a few methods, we keep the results clear and focused on the most important examples. This example shows how the length function can work with a custom object by using a special length method. When we apply the length function to Alice's bank account, it calls the custom method defined in the bank account class. That method treats the account balance in dollars as the length and converts it to an integer. The printed result is the account's balance represented as a length value. When you print an object in this example, Python uses a special method called repr to create a human-readable description of it. For the Alice bank account object, Python automatically calls the repr method defined in the bank account class. That method returns a string with the owner's name and the balance in dollars. This makes it easy to quickly understand the current state of the account object. This example shows how we customize the addition operation for a bank account class using a special method. When we add Alice's account to Bob's account, this method is called and takes the two account objects as input. It then creates and returns a new bank account whose owner is the first account, Alice, and whose balance is the sum of both original balances. When we print this combined account, another special method provides a clear, readable description of the account details. This script introduces Python dunder methods by comparing a built-in list with a custom bank account class. It first inspects a list of temperatures to show that built-in types have many special methods, and filters this list to focus on the dunder methods. Then, it defines a bank account class that implements special methods for representation, length, and addition. With two example accounts for Alice and Bob, it shows that the length function can return the balance as an integer. Printing the account produces a readable description, and adding two accounts combines their balances. Overall, it demonstrates how dunder methods let custom objects behave like built-in types in a natural and intuitive way. Inspecting with Vars. Object attributes with Vars. In dynamic languages, it is often useful to quickly see what data an object holds. The Vars function provides this by showing the object's attribute dictionary, which maps attribute names to their current values. For user-defined classes, this usually includes things like configuration settings or cached results. You can think of it as the object's internal ledger of attributes and values, which is especially helpful when exploring unfamiliar code or debugging, because it lets you confirm what attributes exist and what they contain without searching through class definitions or tracking every assignment. You can think of an object's attributes as a dynamic namespace that you can inspect to understand what data it holds and how it behaves. In an e-commerce system, checking a customer object might reveal fields like name, email, and loyalty points, which helps you verify that the data is correct and see how different parts of the system interact. In data science, inspecting a model object can show its parameters and metrics, supporting result reproduction and comparison. Overall, this turns an object's complex internals into a clear, readable structure that serves as a powerful diagnostic tool for understanding and debugging. The Vars function only returns attributes that are stored directly on an individual object, not those defined on its class or created dynamically. You can think of it as a snapshot of the object's current instance-specific state. Because of this, it is useful for tracking how an object's state changes over time, comparing different instances, and designing classes that are easier to understand and maintain. Python code, object attributes with Vars. Use the Vars function to clearly see an object's instance attributes, meaning the data stored specifically on that instance. First, call Vars to view the current attributes and their values. Then, change one or more attributes and call Vars again to compare the output. This before and after view highlights how Vars reflects only the instance's own stored data and how it updates as those attributes change. We define a customer class to represent a customer with specific information. Its constructor runs automatically when a new customer is created and expects two inputs: the customer's name and state. Inside this constructor, we store the provided name and state as attributes of that customer, and we also set the customer's loyalty points to 0. This way, each customer object keeps its own name, state, and current loyalty points separately from other customers. The add purchase method takes the amount of money a customer spends and uses it to update their loyalty points. It converts the dollar spent to an integer and adds that value to the customer's existing points. This increases the customer's loyalty points in direct proportion to their spending, helping to reward and encourage repeat purchases. We create a new customer named Alice, set her state to Texas, and she starts with default values, such as 0 loyalty points. We then add a new attribute for her last order total and set it to 59.99 to record the amount of her most recent purchase. Next, we add another attribute for her favorite store zip code and set it to 73301. These extra attributes apply only to Alice and show how we can dynamically attach new pieces of data to a specific customer instance. We begin by printing a short message to signal that we are about to show the customer's current attributes, which sets the context for the output. Then we use a built-in function that returns a dictionary of all instance attributes for this specific customer. This dictionary includes values such as the customer's name, state, loyalty points, and any extra details like the last order total and favorite store zip code. Seeing this dictionary lets us clearly understand the customer's current data before making any further changes. A purchase method is called with a value of 40, which increases the customer's loyalty points by that amount and updates their reward balance. After this transaction, a new attribute named status is added to the customer object and set to gold member. This status likely indicates a higher tier in the loyalty program that reflects the customer's improved standing after the purchase. The code first prints a message to confirm that the customer attributes have been updated. It then calls a built-in function that returns all the current instance attributes for that customer. This output reflects any changes made after the object was created, such as added loyalty points or a new status attribute. In this way, the function clearly shows how the customer object's data has evolved over time. This example shows how the Vars function in Python reveals the attributes of an object instance. A customer object is created with several attributes, such as name, state, loyalty points, last order total, and favorite store zip code. When Vars is called, it returns a dictionary of these attributes and their current values. After a purchase is recorded, which increases the loyalty points, and a new status attribute is added. Calling Vars again shows the updated set of attributes and values. This demonstrates that Vars provides a snapshot of the instance-specific data and reflects any changes made to the object over time. Module namespaces with Vars. When working with modules, it can be useful to see everything they define in one place. The Vars function does this by returning the module's namespace as a mapping from names to the objects they refer to. You can think of a module as a container that holds functions, classes, constants, and imported items. And Vars exposes this container in a dictionary-like form. This helps you explore libraries, review what your own module currently contains, and understand which names are available while your code is running. Using the Vars function on a module gives you a live view of its namespace, so you can see what names it currently defines and how it is being used. This helps you track which helper functions and configuration objects exist, and distinguish between items imported from elsewhere and those created within the module over time. In larger projects such as data analysis pipelines or web applications, examining the namespace helps confirm that environment-specific settings are loaded correctly and that sensitive data is not exposed. This kind of introspection can also reveal naming conflicts, unused definitions, or unexpected imports that might otherwise cause subtle bugs. Seeing a module's namespace as a dynamic mapping, which you can inspect with the Vars function, helps you understand more advanced design patterns. Frameworks and plugins often scan this namespace to discover user-defined elements, such as hooks or command handlers, and testing tools may locate tests by matching naming patterns there. In scientific computing, a driver program can read variables from a module's namespace to configure a simulation. Overall, this shows that a module is not just static code, but a flexible, inspectable namespace that supports complex and dynamic designs. Python code, module namespaces with Vars. This example shows how a module's namespace is represented using the Vars function. By applying Vars to a simple custom module, you can see its attributes stored inside a mapping dictionary. The demonstration focuses on how these attributes appear in that dictionary, and then filters and prints only selected names, so the output stays short and easy to read. We import the types module and give it a shorter alias to make the code easier to work with. Using an alias lets us refer to the module with a simpler name instead of typing the full name each time. This is especially helpful when we need to create module objects later in the code. Overall, the alias keeps the code cleaner and more readable. In this example, we create a new module object at runtime using the module type from the types library, giving it the name Utilities module. This lets us define a module on the fly instead of relying only on modules stored in separate files. Once created, this dynamic module can be filled with attributes and functions as needed. It is a convenient way to organize code into clear namespaces without changing the file structure of the project. In this part of the code, we add a few simple data attributes to a custom module called the Utilities module. We create one attribute that stores a speed limit value of 65 miles per hour, and another that stores a city name set to Springfield. These values become part of the module's namespace, so they can be used as basic configuration or shared data wherever the module is imported. This line prints all the attribute names defined in the Utilities module. It does this by using the Vars function to access the module's namespace, which is stored as a dictionary of its attributes. The keys of this dictionary are then converted to a list, giving you a clear list of all names currently defined in the module. This includes both user-defined attributes and special double underscore or dunder attributes. We use a dictionary comprehension to build a filtered view of a module's namespace. Using the Vars function, we get a dictionary of all the module's attributes as name and value pairs. We then keep only those names that do not start with double underscores, which usually mark special or private attributes. This filtering leaves us with a cleaner mapping that focuses on user-defined attributes and makes the module's contents easier to work with. The code first prints a message explaining that it will show a filtered view of the module's namespace. It then displays a dictionary that includes only the user-defined attributes, leaving out special or double underscore names. This focuses attention on the meaningful attributes that were added to the module. As a result, the output is more concise and easier to interpret. This script shows how to create a module dynamically in Python using the types module. It builds a simple module called Utilities module and adds two custom attributes, a speed limit and a city name. The code then prints all attribute names in the module's namespace and filters out the special double underscore names. The final result is a dictionary that contains only the user-defined attributes, giving a clear view of the meaningful content of the module without the internal Python details. Vars and dunder dict. When you call the function that retrieves an object's attributes, it is closely tied to the special double underscore dictionary attribute. For most user-defined objects, this function is simply a convenient way to access the internal dictionary that stores attribute names and values. Asking for an object's attributes without extra arguments usually returns the same mapping found in that internal dictionary. The function and the dictionary, therefore, show the same data from two angles, one as a general inspection tool and the other as a low-level implementation detail. This explains why any change made through one is immediately visible through the other, and highlights their role in Python's flexible object model. When choosing between using the attribute access function and directly working with the special dictionary of an object, focus on their different roles. The function is the safer, more standard way to access and modify attributes, and it works even when attributes are not stored in a normal dictionary. Directly editing the special dictionary gives low-level control and can quickly add attributes, but it also increases the risk of messy, hard-to-maintain code. In general, rely on the function for everyday attribute access and reserve direct dictionary manipulation for rare, carefully considered situations where you truly need that level of control. Use the general attribute inspection function as your main tool for viewing and lightly adjusting an object's attributes, and reserve direct changes to the internal attribute dictionary for rare, well-justified cases. In data analysis, this means you can quickly check what attributes a dataset has, for example, when logging or debugging. In more specialized systems, such as plugins or form builders, you might carefully modify the internal dictionary to add fields or behaviors at runtime. By understanding how the inspection function relates to the internal dictionary, you can explore objects broadly while still making precise, maintainable changes when needed. Python code, Vars and dict. We want to show how the Vars function relates to the special dictionary attribute on simple objects. In many cases, calling Vars on an object returns the same internal mapping of its attributes. This means that when you change the data through one of these views, the change is immediately visible through the other. Together, they provide two closely linked ways to inspect and modify an object's attributes. We define a class called car to represent a car with specific attributes. Inside this class, the initialization method, or constructor, runs automatically when a new car object is created. It takes three inputs: a reference to the current object, the car's make, and its mileage. The method then stores the make and mileage as attributes of that particular car object, so each instance keeps track of its own brand and miles. We create a car object with its make set to Ford and its mileage set to 12,000, which initializes these values as the object's attributes. We then display the object's current attributes using the Vars function, which shows them in a dictionary-like form. After that, we access the object's internal attribute dictionary directly using its special dictionary attribute and print the same information. This shows that both approaches reveal the same underlying attribute data for the object. We use the Vars function to view the attributes of the car object, which gives us direct access to its internal dictionary of data. By adding a new key and value to this view, we set an owner attribute with the value Alice. Because Vars returns a direct reference to the object's internal state, this change immediately updates the car object itself. When we print the attributes afterward, we can see that the owner attribute has been successfully added. We change the miles attribute of the car object by directly updating its internal dictionary, setting it to 15,000. This shows that an object's special dictionary attribute is the actual storage for its instance variables and can be modified to change them. After making this change, we call the function that returns the object's attributes, and it immediately shows the updated value. This confirms that both the internal dictionary and the attributes view reflect the same live state of the object. We start by importing the Math module, which gives us access to many mathematical tools. Using a function that returns the module's internal dictionary, we obtain all its available attributes and methods. We then turn the dictionary's keys into a list. Take only the first 3 entries and print them. This provides a small sample of the kinds of attributes offered by the Math module. This script shows how the Vars function and the special dictionary attribute in Python both expose the same internal state of an object. For a car object with attributes such as make and miles, both tools initially display the same mapping of attribute names to values. When you add a new attribute through the view returned by Vars, that attribute immediately appears on the object itself. And changing an existing attribute through the dictionary view is also reflected in Vars. This demonstrates that Vars and the special dictionary attribute are simply 2 ways of viewing and modifying the same underlying data. The script also briefly illustrates that you can use Vars on a module, such as the Math module, to inspect its available names by listing some of its keys. Mastering help. Using help interactively. The interactive help system acts as a built-in guide while you work in a notebook or at the prompt. Whenever you are unsure about what a function does, what arguments it takes, or how a type behaves, you can ask for help on that object to see clear, structured documentation. This is especially useful when exploring new libraries or checking how specific methods work, because it lets you stay focused without leaving your coding environment. Over time, using this help system turns your environment into a kind of conversational partner that supports your learning as you ask questions and refine your understanding. Use interactive help as a regular part of your workflow, not just when you are completely stuck. When you see an unfamiliar error, look up the function or data type it mentions so you understand what it expects and why it failed. This is especially important in areas like finance or machine learning, where similar-sounding functions can behave differently and lead to mistakes with data formats or parameters. By consulting help often, you build a mental map of the available tools and their proper use, which makes you faster and more confident when solving problems or debugging complex systems. Interactive help is a powerful way to learn new libraries and understand large or unfamiliar code bases, especially when documentation is limited. By using it to inspect modules, classes, and functions, you can quickly see their descriptions and parameters. This supports a question-driven learning style, where you explore a module, examine its contents, and then ask for help on the parts you need. Over time, this habit makes you more effective at navigating proprietary tools or custom software, and helps you adapt faster by using interactive help before turning to source code or external materials. Python code, using help interactively. In this segment, we will show how to use the interactive help system inside a simple script to quickly learn what a function does and what parameters it expects. You will see how the help output clearly explains the function's purpose and describes each argument. We will also contrast the uncertainty of guessing how a function works with the reliability of reading the official interactive documentation. By the end, you should understand why using help directly in your script is a faster and more accurate way to explore functions than trial and error. We begin by importing the math module so we can use Python's built-in mathematical functions. This import step makes tools like the square root function available in our program. With the math module included, we can perform various mathematical operations more easily in our code. We begin by exploring the square root function from the math library using an interactive help style. To understand what this function does, we make an educated guess based on a simple example. We imagine a square whose area is 144 square inches and treat this as our starting value. Using the square root function, we then aim to find the length of one side of that square. We use the math library's square root function to find the square root of 144, which gives a side length of 12 inches for a square. We then display this result to the user. Finally, we encourage the user to explore more details about the square root function by using Python's built-in help feature. We first display a message saying we are about to show a brief help summary for the square root function from the math module. Then, we take the documentation text for this function and split it into separate lines. We keep only the first line, which gives a short description of what the function does. Finally, we print this first line to provide a quick overview of the function's purpose. This material explains that you can use the help function in an interactive Python shell to see full documentation for the math square root function. By doing this, you access the official, detailed description instead of relying on a short summary. It then encourages you to try the help function on other built-in Python features, such as strings, lists, or the length function. This promotes a hands-on way to explore and learn about common Python tools directly in the environment where you use them. This script shows how to use Python's help system to better understand functions. It imports the math module, uses the square root function to find that a square with an area of 144 square inches has a side length of 12 inches, and then prints the first line of the function's documentation. The key idea is to rely on the help function to learn what a function does instead of guessing. It encourages you to open a Python shell and use help interactively on functions such as those for strings, lists, or finding length, so you can read the official documentation and better understand their purpose and parameters. Reading docstrings and signatures. When you use the help system on a function, the most important part is the docstring, which is the author's explanation of what the function does. Focus first on the opening sentence, because it usually states the main purpose and what problem the function solves. Then pay attention to how it describes the parameters, including their names, expected values, and whether they are optional or required. This information shows you how to use the function in practical situations and helps you quickly decide if it fits your needs and how it should be used in your program. When you view the help for a function, the signature line shows how to call it by listing the function name and its parameters. This line indicates which parameters are required and which have default values. It can also show whether the function accepts extra positional or keyword arguments, revealing how flexible it is. By understanding this signature, you can see what information you must provide and what options you can adjust to tailor the function to different tasks. Once you understand docstrings and function signatures, you can use them to learn more than just basic usage. The wording of a docstring can hint at how a function works internally, what side effects it has, and what errors it might raise. A signature with many optional parameters suggests a flexible, highly configurable tool, while a simple signature usually indicates a more focused function. Recognizing these patterns helps you choose the right function for tasks like data analysis or transformation, and, over time, makes it easier to learn new libraries directly from their documentation. Python code: reading docstrings and signatures. In this lesson, you will learn how to use the help system to view a function's documentation and its call signature. You will see how parameters and their default values are displayed in that signature, which helps you understand how to call the function correctly. You will also practice reading and interpreting the help output for a simple custom function, so you can quickly find what its arguments do and how to use it. This function converts a distance from miles to feet and can optionally round the result. It uses a fixed conversion value of 5,280 feet in 1 mile, then multiplies the input distance in miles by this value to get feet. If the optional setting to round the result is turned on, it rounds the answer to the nearest whole foot before returning it. Otherwise, it returns the exact calculated value. We begin by printing a short preview of the function, including its name and its parameter list, so it is easy to see what the function is called and what inputs it takes. To do this, we read the function's special name attribute, which gives us the name as text. We then print a description of the function's signature, showing its parameters and any default values. This provides a quick reference for how to call the function and what arguments it expects, which is helpful for anyone using or updating the code. We begin by printing a message to let the user know that a summary of the function's docstring is coming. Next, we take the docstring for the convert miles to feet function and split it at the first period to extract only the opening sentence. This first sentence serves as a concise description of what the function does. Finally, we print this sentence with a period at the end, giving a quick, clear overview of the function's purpose. The code first prints a message to let us know it is about to use the help function to inspect a specific function. It then calls the help function on the convert miles to feet function. This displays the full documentation in the console, including the function's signature and its descriptive docstring. Viewing this information helps us understand how the function works, what parameters it expects, and any additional details the documentation provides. This script shows how to inspect a Python function's name, signature, and documentation using built-in tools. It uses a simple example function that converts miles to feet, with an option to round the result. When run, the script prints the function's name and its parameters with default values, then extracts and displays the first sentence of the function's docstring as a quick summary. It then calls the help system to show the full documentation. including the complete docstring and parameter details. Overall, the exercise demonstrates how to access and interpret function metadata to better understand and document code. Reading help output. The built-in help system presents information in a clear structure, so you can quickly understand new functions and types. At the top, it shows the object's name, what kind of thing it is, such as a function or class, and which module it comes from. It then displays the function or method signature, including parameter names, their order, and any default values, giving you a fast overview of how to call it. This snapshot lets you quickly judge whether the object is suitable for your task before spending time on the detailed documentation. And with practice, you can rapidly decide whether to use it or move on to another option. After the header and signature in a help message, the main body usually comes from the object's documentation string and explains what the function or type does. It describes its purpose, parameters, and return values, and often includes important notes about edge cases, performance, or platform-specific behavior. These notes might cover differences between operating systems or how large numbers are handled. Paying attention to these details is essential to ensure your code behaves correctly and reliably in production across different environments. When you read the help output for a tool or function, pay close attention to the examples, related functions, and implementation notes. Examples show typical ways to use the function, such as how it fits into a workflow or handles errors. The related functions section can guide you to more specialized or safer options, especially for tricky tasks like working with untrusted input. Implementation notes explain performance details and limitations, which matter when working with large datasets or limited resources. By systematically reviewing these parts of the help, you turn it into a powerful resource for mastering your programming tasks. Python code. Reading help output. This section focuses on how to read the help output for built-in functions. It explains how the help display is structured, including the header that identifies the function signature that shows its parameters, and the docstring that describes what it does. A goal is to recognize these key parts and understand their roles without needing to read or recite the full, detailed help text. The code starts by importing the inspect module, which provides tools for examining live objects, such as modules, classes, and functions. In this case, it is used to access a function's documentation string, a short description that explains what the function does. Using this documentation string allows us to understand the function's purpose without reading long help text. This setup prepares the way for later steps that will show how to extract and summarize key information from a function's documentation. We begin by looking at a simple built-in function to learn how to read Python's help output. The example we use is the length function, which returns the size of an object, such as a list or a string. By examining the help information for this function, we can see how Python describes its built-in tools and learn the basic structure of its help documentation. This code uses the inspect library to automatically get the documentation string of a chosen function, such as the built-in length function. It calls the getDoc method from inspect, which extracts the function's docstring as a single formatted string. That string briefly describes what the function does. This lets us access and use a function's documentation in our program, which is helpful for generating help text or summaries without reading the source code ourselves. The code prints a short header that identifies the function being inspected. It uses the special name attribute to get the function's name as a string, and the special module attribute to find out which module the function comes from. It then prints these together so the user can quickly see what function is being analyzed and where it is defined. This example simulates how the help system might display the function signature for the length function. The code prints a line that looks like a typical help header, showing the function name and a single object parameter. It also includes a slash to indicate that this parameter is positional only. Overall, it serves as a quick visual reference for how the function is called and what kind of argument it expects. The code takes the help text for a function and extracts the first sentence of its docstring. It does this by splitting the text at periods, keeping the first part, and then adding a period to finish the sentence. This first sentence serves as a concise summary of what the function does. The code then prints this summary, labeled as the docstring summary, to give a quick overview of the function's purpose. This line stresses that to quickly understand a function, you should focus on three things: its name, its signature, and a short descriptive summary. Together, these give you the essential information without reading long documentation. This makes it easier and faster to navigate and understand built-in functions and other functions in Python. This material explains a script that extracts and summarizes key information from the help output of a built-in Python function, using the length function as an example. The script uses the inspect library to pull the function's documentation string. It then produces a concise result that includes the function's name and module, a simple example of how it is called, and a short summary taken from the first sentence of its documentation. This method shows how you can quickly grasp a function's purpose and usage by focusing on its name, call pattern, and a brief description instead of reading the full, detailed help text. In this lecture, you learn to use dir to list attributes of objects, modules, and classes for exploration and debugging. Apply vars to inspect and manipulate _dict mappings of objects and modules when appropriate. And invoke help to access built-in documentation and understand signatures and usage of functions and types. In the next module, Module 7, we will go over object creation tools.
Thank you for your attention. See you all in the next lecture.